Video 5 of Chapter 3. We're going to extend on to our least squares regression line and talk about a concept called residuals. Now, we can make all the predictions we want with our line of best fit, our LSRL, but chances are our predictions will unfortunately be off. And it's not our fault, it's just that the data is not perfect. So the difference between the actual and the predicted values is how much we were off by, and we call this particular error value a residual. And so the formula for residuals is a pretty easy, simple formula here. It's just your actual minus predicted values for your response variable. So our actual y value minus our predicted y value, our y hat value. And I find this easy to remember because, well, if you're in my class, you are in AP statistics. So that's why you know to take the actual minus the predicted. So in a warm-up problem that we did in class, we discussed a regression line based on a new diet. And so the question is, calculate John's residual after the second weigh-in when he lost 20 pounds. So for those that don't know, X represents the which weigh-in that you're doing here, and each weigh-in is after I believe it was a 4-week period. So after the second weigh-in, that means 8 weeks have really passed, but X is defined as the number of weigh-ins. So really 8 weeks have passed, but we're not going to plug 8 in. And then he actually lost 20 pounds. Well, we're going to use our regression line to figure out how much weight we thought John would have lost after the second weigh-in. So we're really going to plug 2 in for our X, and then we need to figure out what this particular value is. So using my calculator, 1.61 times 2 is 3.22. So then in the end, y hat will be equal to 15.7 minus 3.22. So now let's do a little bit more math. Minus 3.22. And we would have predicted that John would have lost 12.48 pounds. That is our prediction. Now, he actually lost 20 pounds. So the residual, let me clear some space here now. So, no, need a pen. Thank you. Different color. Thank you. His residual is the actual amount of weight he lost, 20 pounds, minus what we believed he would have lost after the second weigh-in. And so that difference is going to be, 7.52 pounds. So we were 7.52 pounds off from what he thought, or what we thought he would have lost after the second weigh-in. One question that pops up typically is, well, what if he only lost 10 pounds when we expected him to lose 12.48 pounds? Then we'd end up with a negative residual. And is that a thing? And yeah, you can have negative residuals. A positive residual means that we under-predicted what we thought was really going to happen. And if we have a negative residual, then we predicted more than what we actually saw happen. So it is perfectly plausible to have positive and negative residuals. Now, residuals look like this graphically when we look at our regression line. And let me explain with my color-coded system here what's really happening. So for any value of x, and let's say we pick this particular value of x down here, using our regression line, we would have predicted, this would have been our predicted value, and if we went over to the y-axis, we would get our y hat. But in actuality, here's where the y value ended up at. So here's the actual y value. And that difference between the actual y and the predicted y is how much our error was, our residual. So this distance, this vertical distance between the actual data point and where it hits the LSRL, that's visually what our residual represents. And this would be a positive residual up here because the actual is more than the predicted. Now notice sometimes our actual number is below the regression line. And so if you were actually calculating this length here, this would end up being a negative residual. And if you had a point right on, if one of these red dots and the green dot coincided, like almost this scenario down here, then we would have a 0 residual because the actual and the predicted would be the same. Okay, so graphically with our regression line, we can see what that residual represents. And it's always that vertical difference. It's never a horizontal difference because we're always trying to predict our response variable, which is on our y-axis. Now, if you remember when a couple videos ago, maybe just last video, we introduced the concept of the least squares regression line. And I didn't talk about it in the previous video, but we never really talked about what do they mean by the least squares regression line. I mean, line of best fit kind of makes sense here. It's kind of the average line that fits our data points, or the trend line, the line that kind of fits the trend of what's happening. But that LSRL is what we're going to discuss next. And we really needed to talk about residuals before we could talk about what the LSRL represents. Now, this is the same picture I showed you before, but now I've got all these squares in here. And where did all these squares come from? Well, this represented that residual, right? That difference between the two. And there's going to be a little residual here, and there's a little bit bigger residual there, and a little bit bigger residual there, and a little bit bigger residual here, residual here, residual here, and residual here. So what would happen if I took all of these residuals, and all of these residuals above the LSRL, these are positive residuals, all the residuals below the regression line are negative residuals? What would happen if I added up all of these positive and negative residuals is I would always get 0, which is why this is the line of best fit. All right. Now, if I wanted to really fully grasp the concept of the least squares regression line, this kind of goes back to the idea of standard deviation. The definition of standard deviation was the average difference between each data point and the mean. But whenever we added up all the differences between our individual data points and the mean, it always added up to be 0 because some of those differences were positive and some were negative, and that same idea holds true here. So to quantify those differences, we squared them. Again, if you think back to the standard deviation formula, it was the sum of each individual data value from the mean, but then we squared those differences so that our negative residuals, and the same idea holds here, all these negative residuals will become positive, and all these positive residuals will stay positive as well. So when we say we're going to square a number, it's almost like we could literally visually see a square. So if you were to take all these residuals and square their value, and then you can visually see a square, that this line, our line of best fit, our LSRL, it produces all of these squares of area, and these squared areas combined create a total amount of squared error. Well, these squared errors all added together is the smallest possible squared error that could exist. If I change this line to be the not line of best fit, then the sum of all these squared errors would become larger. So I can't eliminate all of these squared errors together because I don't have a perfect set of data that's linear. So again, here's that idea of all these other lines could be the line of not best fit. And so let me show you an example of, so in the background, you can kind of see that faded line. That was the line of best fit. So here's this blue line, and it is the line of not best fit. So if I were to look at all of its residuals, and I can see that all of these squares, if I added up all of these areas, it would be a larger area than the sum of all of these squares. And some people might say, but, some of these squares, like that little guy, that's a really small error compared to this one, because that was the one that we were referring to. There was a drastic reduction in that second value's residual. But if you look at all of them combined, all of these squares areas combined is far more than all of these squares areas combined. So again, the least squares regression literally means we need the smallest possible squares from the residuals here. And that is how you create the line of best fit. It is the best possible fit that reduces the amount of error from all of your data points. All right, so new topic. If we graph the explanatory data, versus the residuals. It can tell us very important things about the data. And this particular graph is called a residual plot. Now, typically with a residual plot, you don't see these little lines in here. So don't imagine that you would actually see those. But each of those little lines represents the residual that we calculated earlier. So if I went back and looked at, no, there we go, that picture, all of these distances, nope, not with the line of not best fit, with the line of best fit, there we go. So all of these little vertical differences, if I were to take all of them and create a residual plot, then I get to see all of them collectively together. And that's what this graph represents. So again, you're not going to see all those little lines in your calculator, or if you were to make a residual plot by hand, you wouldn't see all those little pieces. But this just shows you here's where all of your positive residuals are up here above the 0 line, and it's always going to be the x-axis right here. And since you can have positive and negative residuals, then that's why you can go above and below the 0 line here. Now, ideally, a residual plot has roughly as many positive residuals as negative residuals. And so if I looked at this example, there are 4 residuals that are positive, and there are 4 that are negative. Well, hey, that's perfect. That's not even roughly half and half. It is exactly half and half. But sometimes you might have, for instance, let's say 12 positive residuals and 10 negative residuals. Well, that's pretty close to being half and half. And again, what should be true about all of these residuals versus all these residuals is that together, when you add them all up, you should get 0. The main thing you're going to be on the lookout for is you don't want to see patterns. And I'm going to talk about 2 specific patterns that you want to be on the lookout for. Number 3, you want to have relatively small residual values. Now, if we were doing predictions of, say, weight lost, and we don't want to be off by hundreds of pounds if we were talking about weight loss in a diet program. So we want our residuals to be relatively small. And what I mean by that is more of a percentage-wise. We don't want to be we don't want to have a large error, if you will. But if our data represented something that was related to numbers in the thousands or tens of thousands, and then if you said, well, my residual was 100, and you're like, man, 100, that's a big residual. But if it's 100 out of data that's in the thousands or tens of thousands or hundreds of thousands, well, then 100 out of, say, 100,000 really isn't that big of a residual percentage-wise. Number 4, we really don't need any outliers in our residual plot. And for the most part, you're probably not going to have outliers, but sometimes you're going to see maybe, like if this point was really, really far up here, that's going to be something to discuss. Patterns. Here are the 2 types of patterns to be on the lookout for. Sometimes you'll make a residual plot, and you will clearly see a curve pattern, whether it is curved this way or it might be curved the other way. And it's got to be most of the points have to be making this curve pattern. You can't just kind of pick and choose which points make a curve. You can't go back here to say this one and say, oh, but look at these points right here. Boom, Illuminati. It's right there. Kanye said it. I wouldn't just say there's a curve pattern, because what about those other 3 points? So in this example, I wouldn't say there's a curved pattern. In this example, clearly a curved pattern. So this tells us that our original data is not linear. Now, you may make a scatter plot, and you may look at the scatter plot and clearly see the data is not linear. But there might be times where you look at a scatter plot of your data, and you look at it and go, you know what, it looks fairly linear. Well, the residual plot is going to be really the judge of, in the end, is your data truly linear? And if you see that curve pattern in your residual plot, that will let you know for sure if your data is truly not linear. So I've got the scatter plot may not necessarily show a nonlinear relationship like I just mentioned, but the residual plot will tell us the truth. The other kind of pattern is what I would call an increasing or a decreasing residual pattern. And if you look at this residual plot, first notice that the residuals, they're all over the place. Now, we do have some smaller residuals, but we also have some kind of larger residuals. And as the values of x increase, we start to notice that those residuals, the amount of error that we're off by, they start to get smaller and smaller and smaller. Now, this would be what I would call the decreasing residual pattern, where as x get larger, our residuals get smaller, but it could be flipped around this way, where for smaller values of x, we have very little error, but as x gets larger and larger, our predictions start to become more unpredictable. So be on the lookout for one of those patterns. Now, this tells us that our LSRL makes good predictions for only certain values of x. So again, maybe for larger values of x, our residuals are closer to 0. Or if you had the other way around, let me flip it again, then for smaller values of x, we may make some decent predictions, but again, for larger values, it starts to become unpredictable. So overall, a linear model is not entirely appropriate. So if you were asked, is a linear model appropriate in general, you would want to say no. But in the back of your mind, you need to know, well, it's really okay for parts, but not the whole thing. Now, I'm going to quickly show you how to make a residual plot in your calculator. And I would say out of all the things we're going to cover in Chapter 3, this is the one that takes the most kind of legwork in your calculator. So first off, you need to have your data in your lists in your calculator. Okay, so list 1 is my explanatory, list 2 is my response. And so then you need to go to Stat, over to Calc, and do our linear regression command. So this is typically what we would do, right? If we wanted to figure out the slope and the y-intercept for our regression line, this is the same command that we used previously. Now the store regression equation, this is where we absolutely need to put in a y1. So instead of us writing out the regression equation based on what the slope and the y-intercept are from this regression analysis, we're going to tell it to write the regression line, the LSRL. We're going to tell it to go ahead and put it into y1 of our calculator. Now, how do you get this y1 here? Well, you got to go over to your variables button and then go over to the y variable. So you got to slide over to the right, select function, and then y1 is your first option. And that's how you get this y1 in here. If you have an older calculator that doesn't have this nice table here, then when you do linreg 8, then on your calculator screen it says linreg a plus bx, and then you'll have to type out list 1, comma, list 2, comma, and then you have to go find the y1, but this is the same way that you would find y1 if you had an older calculator. And then you can press enter once you've got this set up, or you can go to calculate and then press enter. So here's the slope and the y-intercept, but if you go up to your y equals button in the top left corner, it's going to have taken that slope and y-intercept and it automatically puts it in the y1 for you to graph with your scatter plot if you wanted to see it with your scatter plot. So we absolutely need to have your regression line in the y1 part of your calculator, because if you don't, then the next step we're about to do here is going to cause your calculator to give you an error. So now go back to your lists, and we're going to go to list 3. And list 3 is where we're going to store all of our residuals. Now, if you remember from earlier this video, what was the formula for residuals? It was actual minus predicted. And that's what we're really going to tell list 3 to do. We need the actual y values. So where do I have the actual y values? Was that list 1 or list 2? And list 2 is where we have the actual y values. So up here, you have to put your cursor up here on the L3. You don't want it here in the first entry spot of list 3, but go up to list 3, and we're going to type in list 2, because again, list 2 are the actual y values, and then we're going to subtract away the predicted y values. And this is where our regression line comes into play, because how did we calculate predicted values? We plugged x values into our regression line. So now you need to go find the y1 again, which was, let me backtrack. You got to press the variables button, go over to y variables, select function, and then select y1. And then after that, let me just clear this off here. After you get the y1, then you're going to need to put a parenthesis, and then we need to put the x values in here. So this y1 parenthesis L1, This is kind of like back in your algebra days where you would say f of x. The function is that y1 regression line. The x that we're plugging into the function are all of those numbers in list 1. These are all of our actual x values. So what we're telling the calculator to do is to take all of these numbers, 1 through 6, plug them into the x of the regression line, which we can't really see, and then come up with the predicted values. But then not only just take those predicted values, but subtract them from the actual y values, which are stored in list 2. So once you've done all of this, then your list 3 should look like this. And you should notice a nice mixture of positive and negative residuals. So again, if you get an error when you type this command out, it's probably because you don't have a y1, the correct y1 even, in your calculator. So you'll need to go back and do that linreg command and store the regression equation. That's the main part. Store the regression equation. So we still haven't actually seen the residual plot yet. So now let's go back to second stat plot. This is where we initially found our scatter plot. And so go to, let's say, your first plot, where maybe you still have it on for a scatter plot. Make sure your other plots are off. And in plot 1, we still want the scatter plot selection. And we still want the X list to be list 1, or wherever you put your explanatory data. But instead of the Y list being list 2, we want to graph the residuals. So we want the Y list to be whatever list you used for the residuals. And then again, this is still the explanatory variable. Explanatory, if I can spell explanatory, right? And then you can press graph, and then you might not see anything, and so then you got to go zoom 9. And then here is the residual plot, finally. And if I look at this residual plot, do I see a curve pattern? I don't see all of my points making a upside down curve or a right side up curve. And again, this is where people get crazy and they're like, but look at these points right here. It's making a curve. Now, it's got to be all of them, genius, not just some of them, all of them. And I don't see that increasing, decreasing spread pattern. I don't see all of my points in general growing like this, and I don't see them going the opposite way here. So this is the type of residual plot you want to see. This tells you that a linear model can be appropriate to make predictions with. So now I want to leave you with a couple questions here. So here's another residual plot. And my first question to you is a linear model appropriate based on the below residual plot? Explain why or why not. And the second question I have for you is, what would be the predicted weight loss for this person at the third weigh-in if their actual weight loss is 15 pounds? So we're going back to the weigh-in versus how much you've lost scenario here. So these numbers, 1, 2, 3, 4, 5, 6, 7, these represent the first weigh-in, the second weigh-in, the third weigh-in, the fourth, etc. And these residuals are how many pounds we were off by with our prediction. So you're going to have to use this residual plot with the person at the after the third weigh-in. So we're talking about this, which means we're talking about that point right there in our residual plot. So see if you can come up with their predicted weight loss using that maybe formula residual equals actual minus predicted. And that is all for video 5. So I hope you got enough residuals